this is a video on parameter estimation using backfitting, and we're doing an illustration in R. This video is in 3 playlists if you want to search. It's also copied from a book that's called Introduction to Statistical Learning with Applications in R. It's a second edition. It's a free book. I encourage you to search it and look through the book. It's an amazing book. We're in chapter 7 when we're talking about generalized additive models, and it mentions that backfitting is usually the technique that's used to estimate the parameters. Now here in part 1 we look at a multiple linear regression where we can't do multiple linear regression. We can only do simple linear regression. And how do we do this? Part 1 we looked at question 11, where we had 2 predictors, and in this part 2 we're going to do it with 100 predictors. So I'm forwarding down to question 12, and this is copied straight from the book. It's part of the the free book, and everything below here is my attempt to illustrate what we're doing. So it's a continuation of the previous. We have 100 predictors. We want to use multiple linear regression, and to do it we're going to perform simple linear regression, repeatedly use it in this what's called a backfitting procedure. And it says how many backfitting iterations required to order good estimates, create a plot, regression coefficients. Okay, so this is the general algorithm, and again everything below is what I created. We want to fit a model, a multiple linear regression model with 100 predictors, and we can only use simple linear regression. So what we do is we come up with initial estimates for the betas, not beta 1. So beta 2, beta 3, beta 100, we have values or initial guesses for those. That's what these represent. We take those to the other side of the model, which is what we're doing here. And so this is the new y, call it y star. And we run simple linear regression to estimate this beta 1 parameter. Now, once we come up with an estimate for that, we subtract it to the other side, and we take this parameter back to this side. And this is what it represents. So we've just estimated beta 1 using backfitting. These are still initial guesses or estimates. Now we use simple linear regression to estimate beta 2. Then we take it and put it in the model, and then we take this and bring it over, and we do that 100 times until we come up with our first iteration of backfitted parameter estimates. And then we use those as our initial guesses, and then we repeat this process. We keep going and going until there's some sort of convergence on the betas. And so here is a program, an R program that we wrote. I set a seed for reproducible results. P is the number of predictors, N is the number of observations. We randomly pick 101 predictors, right? Because we have 100 predictors, but then beta naught needs to be included in our parameter estimates. So that's what we do. We randomly pick it. We randomly have noise. We randomly generate data, X datas, and then we use our beta estimates and our X's to generate Y. So if we think about it, in our data we have X or Y that was generated using this equation. We have X1, X2, ... up to X100, right? We fit a multiple linear regression model. We store it in this object. We find its coefficients, and then we're going to use those to compare how the backfitting procedure performed. Here I do 100 loops. Now technically you shouldn't do it based on a number of loops. You should do it based upon how well your beta parameters are converging, and then set some sort of tolerance or convergence criteria and stop it when that's met. or if you go over some maximum number of loops. Now here I'm going to store our beta parameters in these two objects. Beta is a matrix, has 100 columns, and it has n and the number of rows is how many loops we do, right? And that corresponds to every, the backfitting loops that we do. So every loop, the beta coefficients, we're going to hope start to converge to something. And I keep beta 0 separately, mainly just that's the way I started this program, and so it was easier to think about. Plus, I think it was easier to think about the indexing if I kept beta 0 separately. So this is what we have so far. Okay, we have the first column is beta 1, so this is the beta. The second column is beta 2, and then we're just going to keep going until we get to beta 100. And the rows, this will be 1, and those correspond to iterations, or the number of loops. And so the last one is 50. That's what I set our tolerance at, or not a tolerance, but how many loops we're going to do. Then we have to put initial guesses here. And I just use 0. And it really doesn't matter. Okay. So the idea is we fix these values, and then we run simple linear regression to estimate that. Then we fix it, and then we try to estimate this parameter. So that one's estimated. Then once we have an estimate for that, we take it to the other side, and we estimate x3, and we keep going. Then we use these as our initial guesses, and then we rerun the backfitting procedure again, one at a time, estimating these. And then we continue it for 100 times. So this right here, this tells us how many loops we're doing, which is going this way. And then we have to loop across each column, and then this is what we do. So we run multiple linear regression, and these are the x's. So we start at column 1, so we want all the columns moved to the left side of the equation. So that's what this represents, all the columns but that first one. And then we, of course, take it times the beta parameter estimates, which is 0, the first iteration, and we model it on just this first column, right? K is 1 initially. And boom, it's updated right there. And then we're still in this loop here. So then K goes to 2, and it's everything is modeled or taken to the left side except for the second column, and then linear regression. So we estimate it, and we go down. And then once we get out of that loop to estimate the beta 0 parameter, we have estimates for all the betas, right? And we take it times our X data set. Remember, we're still in the first loop, right? So we're estimating beta 0, which is this variable right there, and we put it in the first iteration. What this does is it copies our estimates in this first row to the second row. So we start out with those, and then we go to loop 2, and then we cycle through each column, estimating each column one at a time, and then we estimate beta 0. Then it copies these to the next row, which would be 3, and then it loops, goes through the columns, and it just one at a time goes down. And it's actually really fast, because simple linear regression is fast. So these are our estimates, and it contains, so beta is a 50 by 100 matrix. Beta 0 is going to just be a 50 by 1 matrix. So the columns here is all the betas. Now what the sweep function does, it repeats the same operation across a dimension. So sweep over the columns, and we're going to subtract out the multiple linear regression coefficients. So that's an error. We're going to square it. So it's the squared error. So this is a matrix where we've subtracted the least squares coefficient from its estimate, and then we square it. So this is still technically a 50 by 51 matrix, right? This number of loops, 101, I'm sorry, because that's how many parameters. Now I'm going to apply in this matrix, and I want to find over the rows, I'm finding the maximum squared error. And then I'm just going to look at the last one just for fun. There it is. That's 26 zeros. So that's like converged so quickly. And if we look at the maximum by loop iteration, that's what this plot is. So we're within or less than 10, and then after the second iteration, or less than 1 is the maximum difference between coefficient and our backfitting, and then it just quickly goes to 0. So the difference between the backfitting estimates and the multiple linear regression estimates, they converge. This one here it's not really a pretty plot, but it illustrates the movement in these beta parameters. So this is the X value, and this is a matrix with and it plots this X value against each column. And that's what this is. And so I kind of like it because you get to see the movement in a beta parameter, and then it goes flat. So there's movement, little movement, and flat movement. So really all the movement is happening within here. If you look closely, there might be something at 4. And so within 3 to 5,